Hello, my name is Piotr. I'm a software engineer at ScyllaDB. In this presentation, I would like to tell you about how we, at ScyllaDB, implemented per-partition limiting, an overload protection feature designed to mitigate negative effects of some pathologies in the workloads. The talk will explain the problem this feature addresses and how the feature works. Furthermore, I will tell about the performance issues related to error reporting in ScyllaDB we uncovered during development and how we addressed them. But first, let's start with a quick recap on ScyllaDB's architecture. ScyllaDB is a distributed database. A single cluster is composed of multiple nodes, and each node is responsible for storing and handling a subset of the total dataset. Furthermore, each node is divided into shards. A single shard is basically a CPU core with a chunk of RAM assigned to it. Each shard of the node handles a subset of the data the node is responsible for, which means that the CPU cores rarely have to communicate with each other, minimizing the cross-core synchronization cost. All of this makes ScyllaDB not only horizontally scalable, but vertically scalable as well. The most granular unit of partitioning is, well, called a partition. A partition in a table is a set of all rows which share the same partition key. For each partition, a set of replica nodes is chosen. Each of the replicas is responsible for storing a copy of the partition. While read and write requests can be handled by non-replica nodes too, the coordinator needs to contact the replicas in order to execute the operation. Replicas are equal in importance and, depending on the consistency requirements of the user, not all have to be available in order to handle the operation. This data partitioning scheme works well when the data and load are evenly distributed across all partitions in the cluster. However, a problem can occur when one partition suddenly starts receiving a disproportionate amount of traffic compared to other partitions. Because ScyllaDB assigns only a part of its computing resources to each partition, the shards on replicas responsible for that partition can easily become overloaded. The architecture doesn't really allow other shards or nodes to come to the rescue. Therefore, even a powerful cluster will struggle to serve requests to that partition. We call this situation a hot partition problem. What's more is that the negative effects aren't restricted to a single partition. Each shard is responsible for handling many partitions, so if one of them becomes hot, then the partitions which share at least one replica shard will be affected too. Sometimes hot partitions may appear because the cluster schema does not fit your data. You need to be aware of how your data is distributed and how it is accessed and used. Then model it appropriately so that it fits ScyllaDB's strengths and avoids its weaknesses. Unfortunately, the responsibility lies within the system designer. ScyllaDB won't repartition the data automatically for you. While it makes sense to optimize your data layout for the common case, however, the uncommon case will inevitably happen. For example, your users will not always behave as expected, so it's very important that their behavior does not bring the whole system to a grinding halt. What's more, the source of the problem may not only originate from outside of your system, but also from the inside. No matter how well we test our code, bugs do happen and may cause some parts of the system go crazy, leading to highly unbalanced workloads. Therefore, it's not only important to think about the overload protection at the system level, but at the per-component level as well. The core of the issue of hot partitions is that requests are incoming with a greater rate than the replica shards are able to process them. The requests form a queue which keeps growing. As the queue grows, requests need to wait longer and longer, ultimately reaching a point where most of them fail due to them timing out before they even start being processed. The system has good throughput because it accepts a lot of work, but poor Goodput, as most of the work will ultimately be wasted. The problem can be mitigated by rejecting some of the requests when we have reasons to believe that we won't be able to process all of them. Requests should be rejected as early as possible and as cheaply as possible in order to leave the most computing power for the remaining requests. While it is not always possible to correctly estimate the impact a single query will have on the replicas, we can apply some heuristics to decide whether we will be able to handle it. Let's say that we don't expect more than X writes per second to any particular partition. In ScyllaDB 5.1, we implemented per-partition rate limiting, which follows that idea. For a given table, you will be able to specify a per-partition rate limit, separately for reads and writes. If the cluster detects that reads or writes for a given partition start exceeding user-defined limit, it will start rejecting some of the requests in an attempt to keep the rate of unrejected requests below the limit. While the feature tries to accurately apply the defined limit, due to the distributed nature of ScyllaDB, the actual rate of accepted requests may be slightly higher. Keep in mind that this feature is not meant for enforcing strict limits, for example for API purposes, but was rather designed as an overload protection mechanism. The inaccuracies are there due to the details of the implementation and will be explained in the next section. So now I will explain how the feature works. Let's start with a very simple case. A cluster composed of a single node with a single shard. The shard maintains a set of hit counters for each partition, or rather token, which is the hash of a partition key. When a partition is accessed, its hit count is incremented. Every second, the values of all counters are halved, and those which drop to 0 are removed from the set. Because of this exponential decay, the number of counters with non-zero values is usually pretty small and fits in a statically allocated hash map. Notice that when a rate of requests to a single partition is stable, let's say X requests per second, the partition's counter will eventually start oscillating between X and 2X. Nodes use that observation to estimate the current request rate, and if the request rate is above the limit, requests will be rejected with a probability such that the unrejected request rate should drop below the limit. Now we need to extend this algorithm so that it works in general case, with more than one node in the cluster, each node having multiple shards. The situation becomes more complicated. First, in a ScyllaDB cluster, all shards are capable of handling requests for any partition. The shard handling the request, the coordinator, communicates with the replica shards and asks them to either modify or read the current data of the partition. As I mentioned before, rate limiting works best if rejection is done as early as possible, so it would be best if the coordinator did it. Unfortunately, this can't be done reliably in general case. A single cluster can have hundreds of shards, and operations on a single partition may be coordinated from any one of them. Getting an accurate estimation of the rate would require communicating with all shards. We can also extrapolate the rate of requests from the coordinator of the current request, as we don't know how the clients choose the coordinators. Although we usually recommend users to use shard-aware drivers, which always choose a coordinator from a small set of replica shards, other drivers may choose coordinators randomly, and we would like to support them too. Because of these problems, we decided to count per-partition operations on replicas and make them responsible for deciding whether the operation should be rejected or not. Each replica makes its decision independently without communicating with others, so it is possible for some replicas to accept while others reject. This can lead to wasted work because, depending on the consistency level chosen by the user, we require a minimum number of successful replicas in order for the whole operation to succeed. We minimize the chance of disagreement happening like this. The coordinator chooses a random number between 0 and 1 and sends it along with the request to replicas. Replicas compute the probability of acceptance and reject only if the random number is above the computed probability. The probability directly depends on the current value of the partition's hit count on the replica, but they are usually very close to each other on the replicas. Finally, there is an important special case. I said that we don't allow coordinators to reject in general because hit counts are tracked on replicas. However, what if the coordinator is a replica? In that case, we lift this decision from replicas and actually allow the coordinator to decide whether to accept or not. Okay, sorry, I will have to start this slide again. So, finally, there is an important special case. I said that we don't allow coordinators to reject in general because hit counts are tracked on replicas. However, what if the coordinator is a replica? In that case, we lift this decision from replicas and actually allow the coordinator to decide whether to accept or to reject. If it accepts, it tells other nodes to account the operation and they must unconditionally accept it. If it rejects, it skips sending anything to the replicas altogether. While this leads to some requests being undercounted, this error isn't actually very big in practice and rejecting is much, much cheaper. The special case described here is actually the common case when you are using shard-aware drivers. We highly recommend using them anyway, but now you have another reason. Initially, after coding the solution, we found that the performance wasn't as good as expected. In a local benchmark, we actually achieved an opposite effect. Rejected operations took more CPU than the successful ones. This was very strange because tracking per-partition hit counts wasn't expected to be compute intensive. It turned out that the problem was related to how ScyllaDB reports failures, namely via C++ exceptions. So what are the problems with exceptions? Exceptions are a bit notorious in the C++ community. There are many problems with their design, but they are most commonly criticized for bloating binaries with program metadata necessary for exception handling, and that the program performance when an exception is thrown can be hard to predict. Some of the projects using C++ go as far as to disable exceptions altogether due to these reasons. On the other hand, it's hard to avoid exceptions because they are thrown by the standard library and because of their interaction with other language features. Our asynchronous framework, Seastar, embraces exceptions and provides facilities for handling them correctly. ScyllaDB is built upon Seastar, so we got used to reporting failures via exceptions. They work fine, provided that errors aren't very frequent. However, during overload, this assumption is no longer true, and we notice that throwing exceptions can introduce a performance bottleneck. This problem affects both existing errors, such as timeouts, and as well as the new rate limit exception that we tried to introduce. We had some performance issues before with exceptions. In libstd C++, the standard library for GCC, throwing an exception involves acquiring a global mutex. That mutex protects the global list of objects, data structures containing information about the code loaded into the process, including unwind tables necessary for the runtime to perform exception throwing. This list is updated when dynamic libraries are loaded or unloaded from the process, therefore it needs protections from concurrent access. However, ScyllaDB doesn't use any dynamic libraries, so we were able to disable the mutex using some clever workarounds. However, as a side effect, we also disabled a global cache, which speeds up the process of throwing exceptions. In the end, it was a positive result for us because although exceptions were slow to throw, they became scalable. Exceptions are usually propagated up the call stack until a try-catch block is encountered. However, in programs with non-standard control flow, it sometimes makes sense to capture the exception and rethrow it elsewhere. For this purpose, std_exception_ptr can be used. Our asynchronous framework, Seastar, is a good example of code that uses this. Seastar allows running concurrent, asynchronous tasks which can wait for the results of each other via objects called futures. If a task results in an exception, it is stored in a future using std_exception_ptr and can be later inspected by a different task. What is nice is that Seastar reduces the time spent in the exception handling runtime. In most cases, Seastar is not interested in the exception itself, but only whether a given future contains an exception or not. Because of that, the common control flow primitives such as then, finally, etc. do not have to rethrow and expect the exception. They just only check whether an exception is there. In addition to this, it is possible to construct an exceptional future directly without showing the exception. Unfortunately, the standard library doesn't make it possible to inspect an STD exception PTR without rethrowing it, because each exception has to be inspected and handled appropriately at some point, sometimes more than once. It is impossible for us to get rid of throws if we want to use exceptions and have portable code. We had to provide a cheaper way to return timeouts and rate limit exceptions, and we tried two approaches. The first approach that we explored was quite heavy-handed. It involved plowing through the code and changing all important functions to return a boost result, which is a type from the boost outcome library that holds either a successful result or an error. We also introduced a custom container for handling exceptions, which allows expecting the exception inside it without having to rethrow it, unlike STD exception PTR. This approach worked, but had numerous drawbacks. First, it requires a lot of work in order to adapt the existing code. Return types had to be changed, and the boost results returned by the functions had to be explicitly checked, whether they hold an exception or not. Moreover, those checks introduce a slight overhead on the happy path. We applied this approach to the coordinator logic. The other approach that we used was to implement inspecting the value of STD exception PTR ourselves. We encountered a proposal to extend the STD exception PTR's interface, and the interface included possibility to inspect its value without rethrowing it. The proposal actually includes an experimental implementation which uses standard library-specific and ABI-specific constructs to implement it for some of the major compilers. Inspired by it, we implemented a small utility function which allows to match on the exceptions type and expect its value, and replace a bunch of try-catch blocks with it. We got rid of throws in the most important parts of the replica logic in this way. It was much less work to do than the previous approach, as we only had to get rid of try-catch blocks and make sure that exceptions are propagated using the existing non-throwing primitives. While the solution is not portable, we use and support only a single toolchain at a time to build ScyllaDB, and it works for us. And now, let's see some results. We conducted two benchmarks to show the benefits of our improvements, one for per-partition rate limiting and one for the speedups in exception handling. Here is a benchmark that demonstrates the usefulness of per-partition rate limiting. We have set up a cluster on AWS consisting of three i3.4x large nodes with ScyllaDB 5.1.0 release candidate 1. We prepopulated it with a small dataset which fits in memory. Then we run a uniform read workload of 80k reads per second from a C5.4x large instance. This represents the first section of the charts. Important note, charts show per-shard measurements. Next, we start another loader instance, but instead of reading uniformly, it performs heavy queries on a single partition only, with 8 times as much concurrency and 10 times the data fetched for each read. As expected, free shards became overloaded. Because the benchmarking application uses fixed concurrency, it becomes bottlenecked on the overloaded charts, and its read throughput drops from 80k to just 26k requests per second. Finally, we apply a per-partition limit of 10 reads per second to the table, and we can see that the throughput recovers. Even though the shards that were previously overloaded now coordinate many more requests per second, nearly all of the problematic requests are rejected, which is much cheaper than trying to actually handle them, and is still within the capabilities of the shards. Next, here is another benchmark that demonstrates better stability due to optimizations on the exception handling path. A free-node cluster, similar to the previous one, was subjected to a write workload to a single partition. The data included in each request is very small, so the workload is not I/O bound, but rather CPU bound. And each request has a very small server-side timeout of 10 milliseconds. The benchmarking application gradually increases its write rate from 50K writes per second to 100K. And we can observe what happens when ScyllaDB is no longer able to handle the throughput. The slide actually shows two runs of the same benchmark, superimposed on the same charts. One for ScyllaDB 5.0.3, which handles timeouts in the old slow way, and the other for ScyllaDB 5.1.0 release candidate 1, which has exception handling improvements. We can see that the older version of ScyllaDB gets overwhelmed somewhere around the 60K writes per second mark. We are pushing the shard to its limit. Because we have set a short timeout, some requests will inevitably fail. Due to the fact that processing timed out requests is more costly than a regular request, the shard very quickly enters a state where all requests that it processes result in timeouts. The new version, which has better exception handling performance, is able to sustain a larger throughput. Some timeouts do occur, but they do not overwhelm the shard completely. Only at the 100K requests per second mark, timeouts start to be more prominent. Thank you for your attention.